welcome to the Clinician Engineer Hub, the online coffee and cake evening. Thanks for coming. First off, I think the idea is it's a kind of casual conversation with a few speakers we can hear from. I've made a lemon drizzle cake, and I've not got a coffee. It's a warm drink though, so I think I'm there in spirit. We hope that this sort of facilitates a bit of discussion. So definitely, if you've got any questions for the speakers, just put them in the chat, and after the speakers are done talking, we can go through those. And feel free to turn your cameras on if you want, but maybe not unmute yourself always. So yeah, the Clinician Engineer Hub is a group that is working to sort of put on a lot of these events, trying to connect clinicians and engineers to, well, clinicians and engineers. And hopefully today we see how we can work together, basically. The format of the event, don't know why that's as follows. Do you guys have a window blocking the screen? If not, then
no, it's perfect.
Great. Okay, so we've got Mr. Chris Coulson speaking first, and then Dr. Angela Kedgley, and then Professor Peter Childs. And I'll hand over to Michael, who can introduce. Chris.
Thanks very much. Thanks for the introductions, and thanks to the three speakers. Mr. Coulson very kindly agreed to come and talk today. He's a otology and skull-based surgeon that I met in Birmingham last year. But he's also the founder of Endoscope Eye, which I think is going to form the basis of his talk tonight. And secondly, he works around tech quite a lot. He's the editor for ENT and Audiology News, the tech editor. And less famously, he's one half of the Guinness World Record for holding the fastest marathon time in a two-person outfit, which is also very impressive. It's amazing what you can find by Googling people these days, Mr. Coulson. So I hand over to you, sir.
Oh, well, thank you. A lovely intro. Well, thank you for the invite, and hope our story of what we've done up to now interests you. Let me get my presentation up. Can you all see that okay? Yeah, okay, great. So I want to talk about innovating in healthcare and kind of beyond. So as Mike said, I'm an ear consultant in Birmingham. And actually during my training, I undertook a PhD in robotic cochlear implantation, which is putting an electrode into the inner ear to allow people who can't hear to hear. Now, obviously, I didn't do the engineering bit of this. I was on the clinical side, but I became kind of good friends with a good number of engineers, and actually realised how much they have to offer us. And actually, that interest has kind of taken me through my career in innovation. And actually, without it, I don't think I actually ever would have started. So this is the hospital that I work in, and indeed Mike used to work in. So Endoscope Eye was born out of this. So when I first begun as a consultant, it was 2011, and most of our note keeping was on paper. This was a classic note where you write something about the patient, draw a picture of an ear. Since this is what to ear people an ear looks like. This is an ear drum, some of the bones of hearing, and a retraction onto ISJ, incudo-stapedial joint. Then we're going to review them and monitor in 3 months. And you can all see what the problem is with this. Okay, it's on paper, number one. You know, paper's a dying thing within the NHS, and rightly so. It's illegible. Okay, I can just about read it, but I've read it a number of times. The drawings are interesting. So the record we've always kept of a drawing is, I look in someone's ear, I interpret what's wrong, I draw what's wrong. I'm not drawing exactly what I'm seeing. I'm drawing what I think I've diagnosed, and then I make a drawing of that. So it's not, whilst it may be a reasonable record, it's not a very good record. Okay, and the worse you are at diagnosis, almost definitely the worse your drawings will be as an accurate representation of what's happened. It's difficult to share, both with into the notes and with other colleagues, and indeed with the patients. Explaining to patients what's gone wrong is pretty hard, and actually drawing them a picture kind of means nothing to them. So this was 2010, 2011. This is my colleague, Ajith George, who has got a flexible nose endoscope. You can't quite see it. It's going up his nose and it's looking down at his throat. And he's trying to line up his phone with the eyepiece. So there's a normal eyepiece to look down, and he's trying to line it up, and you just about make out his larynx. It's a pretty rubbish image, but you can see where the initial idea came from, that it's not absolutely dreadful, that picture. And Ajith, who's another ear, nose and throat surgeon now in Stoke, did a nice little drawing. Yeah, I can put an adapter on a phone and we can line it up, and that'll be great. And this is where I find almost all clinicians' innovation ends, okay? Which is, I've come up with a good idea, I've got a basic solution, and I have no idea where to go from here. I have no idea how to make this real. And actually, I can only design within the constraints of what I know. And as a clinician, I don't know anything about engineering, do I? I don't know anything about material science. There's so many things that I don't know. I don't know what's available as methods to solve this. So that's where and I'm going to punctuate this with a number of lessons that I've learned, not necessarily that you need to learn. Lesson 1, use experts, okay? Ideally people who are cleverer than you. I don't see the point in me learning how to code things. Whilst I could code to a very, very poor level, I'm sure, you might as well use someone who's an expert in coding, okay? Similar to engineering, I could do some really bad drawings of things, and even these days 3D print something, but it'll never be as good as someone who was an expert in that. And I think you might as well use, from the clinical side, our expertise as the end user who wants things to be as good as possible to help our engineers design as well as possible. Here we go. So that's Ajith on the top left. Mark Prince is our engineer, who's an engineering lecturer at Aston University. And Simon Pargita is our app developer, who used to run a hardware and software company prior to joining us. So these are Mark's original drawings of different ways of solving this. Is on the bottom right, is a collapsible version. And then he printed our first prototype. This is some of our first prototype images, again on a flexible scope. But actually, we thought the big challenge was an engineering challenge, as in a physical device challenge. But actually, the main challenge was getting the camera to work properly. You can see on the left, it's overexposed. It's a small image. And on the right was after we developed our own app to optimize the camera function for endoscopic imaging, so that we can control the exposure and focus and deliver a much bigger zoomed in picture. We then go back to the engineering side. So once we come up with our final design, we initially injection molded our devices, which is an interesting process to go down. Our engineer hadn't ever done this himself before, and now has, which is a good thing. But actually, we've subsequently moved to 3D printing them, as 3D printing has improved in end results. The first few 3D printers we had in those early years were far too rough and ready. Actually, they have now improved quite markedly. So now, with a combination of a app on your phone and an adapter, and this is our final version of our adapter for the older style phone, we clipped it into the speaker slot. It's changed more recently as Apple keep changing their phones. And so we've been making adapters since 2011. So every phone since the iPhone 4S. We only do Apple at the moment for a number of reasons. The first one being cost. So we're a bootstrapped company, i.e. we've just funded it all ourselves. We've had almost no external funding. We've done that for a couple of reasons, principally for control. and actually we've been able to just do what we want when we wanted to, although I accept you need a certain amount of money to get things going, although actually for this phenomenally small amount, and actually our main expense is both the time and indeed the cost of injection molding to start off with. And Apple delivering us 2 phones a year was achievable. And if we then go into Android, where, I don't know, you pick up to 20 phones, we would have been spending an awful lot of money on adapters. There are 3 bits to it. There's a kind of an external ring which compresses, you can just about see here, a collet that just holds the eyepiece of the endoscope in place. And the whole thing, you can't really see it on these pictures, fits onto the phone. And it's the body that fits onto the phone that needs to change with each phone. Adjustable adapters just kind of don't work. You spend too much time fiddling with them to get the alignment with the camera in a perfect position. So it's we then CE marked it, a process we did ourselves. So most of the regulation, and I'll come on to that in a bit, we've just done ourselves. It's a fairly painful exercise, although you learn so much going down it, and it helps you for the subsequent projects. So this is what I now do in clinic. So this is how I examine people's ears. I never use an otoscope, and this I think, and I am biased in this, is an absolute standout imager of an ear. So we're HD imaging onto our phone. This is the malleus here. This is the incus. You can see it so well, and you can't normally see it because the eardrum's sunk back onto it, and it's kind of shrink wrapped around it, and that's why it's so clear. See some bubbles of fluid under here, or just bubbles of air. It's the fluid around it that makes the bubbles. So that's one ear. And this is the other. So this is how I examine everyone's ears. And then I show the patients pictures of their ears. And so I can explain to them what's going on with their ear. Okay. And it makes so much more sense to them when they can see it. And it generally doesn't, even for people who've never looked at an ear before, it's usually really clear what's wrong with them. Okay. This is someone's throat. Now, with an ear endoscope, it's a rigid endoscope, so it's a rod and light construction. So you get better imaging than the flexible endoscopes, which is a fiber optic. It's still pretty good. This little polyp here on this is the vocal cords of the voice of the larynx, and I mean this is a great thing, isn't it? Look at that cyst there. It's the epiglottis here. It's what they're breathing around. They can hardly breathe, hardly a space to breathe here. Okay, and this is a vocal cord palsy. So this side of the voice box isn't working at all. And these make amazing records for people's notes. The other advantage, especially for this middle one, is the classic thing that happens here is the most junior person has gone to see the patient. They've put an endoscope down them. They've then phoned their registrar, who said, "Oh, yeah, you must be wrong," you know. And then the next person puts an endoscope down, okay? And they have 3 or 4 people putting endoscopes down them. And actually, you don't want to fiddle with this, okay? This is very close to blocking off their larynx completely. So it's best that only one person looks at it and then shows someone a video. One of the really interesting things about selling things on a website, which is how we sell all our kit. And in fact, we don't really put adverts out, is you sell to all kinds of people who you didn't expect to. Probably 1/3 of our sales are to vets. Now, the reason vets like it is rather than looking down this endoscope here with and not really having a good look on what the horse is doing, some vets found that they would get kicked every so often, and obviously being kicked by a horse is something you kind of want to avoid. So equine vets in particular like it. We sell to a number of gunsmiths as well for checking out barrels of guns. Lesson 2: if you do something that turns out to be pretty good, then you should probably do something else and not just dwell on it. Lots of innovation, I find, is really obsessed with having a single focus and going for it and not deviating to the side. And I think you learn so many lessons getting to your first innovation, but it seems it seems crazy to me that you don't innovate more and more, as opposed to just stay on that same line and same product. So in my mind, when you're getting images like this, I mean, why do I need to see these people face to face? Okay, what do I need to make a diagnosis? I need that video, I need their history, and I need a hearing test. And actually, I could probably diagnose most things from that. Okay, which then led us on to what we call telescopic referral, which is in essence a combination of endoscope eye and telemedicine. Now, as with everything, there are some boring and necessary hurdles, and I think you just got to keep your main goal in mind. And also, the other useful thing is to start small and gradually grow. So what we did is we put together our kit of an endoscope. This is for someone's ear, a light source, an adapter, a phone, and then a clinician platform to answer referrals on. And we delivered that to a number of GPs in Stoke. It said, at the point of you about to refer someone to secondary care, can you send us the referral? And we did that for 6 months and found that actually we could successfully transact 83% of referrals. So avoiding someone coming into secondary care and dealing with their health problem. The patients loved it. One, they could see a picture of their ear, and two, they got an answer from someone with my job title within a name. I'm not saying it's me, but it's you know, when it says ENT consultants at the bottom, they think, well, at least they've got a proper opinion. Okay, so we started off with that really kind of basic trial. There we go. So we started off with that basic trial to prove the proof of principle. And then our next lesson is you've always got to take it a lot further than you think. You think, oh, I've come up with this great idea. People will love it. Someone will pay us a lot of money for it, and then that'll be it, right? But it's never the case. You have to really spend time and effort and years in this. So actually, having demonstrated the fact that the service works, we're now, in essence, just trying to deliver it in as many hospitals as possible. So we are doing both or all three of ear, nose, and throat referrals. We have a history for all of those, and the examination component for the ear is a video of the ear and a hearing test. The nose is obviously a video of the nose, and a throat video of the throat. So we're now delivering that on a number of hospitals across the UK, and actually, hopefully, that will gradually increase in number over time. And that's our clinician platform. So that's the kind of endoscopic videoing side of things. What I was saying before about being singularly focused, you might miss that shiny thing on the periphery for your view. So if any of you are into cycling, this was from the Tour de France in 2015. Well, I saw someone put an endoscope into someone's bike to look for a hidden motor. So there was a thought that professional cyclists were using hidden motors to speed up their cycling. And they were putting an endoscope, they're taken off the crank here, the pedal arm, and they put an endoscope inside. And I thought this would be a good press opportunity for us to sell some of our adapters. So I contacted the UCI, which are kind of like the FIFA of cycling, and actually got in conversation with them, saying, well, why don't you just screen for this? And they said, well, you can't do. We've tried it. We've tried a number of magnetometers, and they're all too sensitive, and they go off the whole time because of the bits of magnet around the bike. And so I spoke to our engineer and tech guys, and they thought that this could be achieved, and actually fairly simply with essentially the compass in a phone or tablet, and then an extra magnet to create a static magnetic field that when you then came across the battery or motor, you'd see a kind of a regulated deflection, and then an app to regulate that. And we designed something for them, and this was kind of before e-bikes became kind of common. So this is a bike that's been set up with a hidden motor. So you can't see it. It looks like a normal road bike. And this is what they were concerned that people were using. And you can see when they turn it up, it's a fair old rate, isn't it? You know, it'll make a big difference to any professional cyclist. So we went over to the World Cyclocross Championships with our device, and on the third bike we tested, we found a motor. So we've been the suppliers of motor fraud detection devices to the professional cycling world for the past 5 years, which is an interesting little side off. The final device I want to talk about is the SNAP device. So at the beginning of the pandemic, one of the really concerning things for ENT surgeons in general was when you put an endoscope up someone's nose, it often makes them cough. And obviously coughing is aerosol generating and indeed droplet generating. But obviously you can't have a mask on someone because you can't get an endoscope up the nose. And if you stop endoscoping people, you'll miss cancers. So we designed this. We came up with this concept of being able to scope someone through a mask. So we have an inner component with a one-way valve, an external component, and a trocar. And as is always the way, you go through a number of design iterations to get us to the final point. I think actually we kind of had 100 different slight changes in the device until we ended up with our final one we were happy with. And then in the kind of space of 9 months, we went from this never been a problem to ENT people to through conception, design, development, trialing, and we ended up making this and then licensing it to a medical device company to continue to sell. So it actually turns out it isn't needed. As long as clinicians wear a mask, you're fine. But actually, as a project in and of itself, I saw it as a huge success because we've taken a product from concept to market in 9 months, which could have had a huge impact. It turns out that it wasn't needed, but we didn't know that at the beginning. This is just some of our design work. This is the four of us. Oh, I've missed my. So hopefully staying within time. I think you should just do something you love doing. It's going to be a long journey. It's going to be loads of painful bits in there, but it's a wonderful, fun, wonderful world to be in. It's definitely worth it. And you can make some kind of real tangible differences to healthcare and beyond. Thank you.
Thank you, Chris, for the talk. Fantastic. We didn't get any questions into the chat, but fortunately I've made myself a few questions, if you don't mind. I know that we're a bit pushed for time because we started slightly late. The first question I was going to ask is, you were talking about triaging. I wondered if the technology has been used in resource poor areas to try and bring things like head and neck clinics, perhaps in rural areas or places where you don't get frequent clinics. You were talking about if you can scope once and scope well, and then you can see people such as yourself can review those images. If that could be moved to places where it's even harder to get to see an ENT surgeon than Birmingham. Yeah.
I mean, I think this has applications in many places, resource poor and indeed resource rich. I mean, I personally don't really like the concept of triage. I kind of find it's not pointless, but I kind of, as opposed to a triage step, I just prefer a diagnosis and management step. I mean, why, when you have all the information you need to decide what to do, why would you channel them one way or the other? I'd just say, why don't you just treat them? Most people with head and neck cancer symptoms, thankfully, don't have head and neck cancer. So actually, someone with a hoarse voice, you say, okay, one, the good news is you don't have cancer, and two, this is what you need to do for your hoarse voice. And then actually they're then not on another waiting list somewhere. And actually, in a resource poor place, I guess the only difference would be this is more a case of saying you don't have cancer, you're okay. But actually, early diagnosis for everything is the key. I mean, even for kind of ear stuff that I deal with, people are really concerned until they have a diagnosis. You and I might know that there are very few very serious life-threatening problems that affect the ear, but the patient doesn't know that until we tell them. So I'm a big fan of being able to deal with patients as quickly as possible to allay those fears, which in most people is saying essentially you've got something normal going on, be that hearing loss or tinnitus. And for the people who do have something more, being able to optimize their throughput into normal secondary care services, be that, that someone I would normally scan. Okay, well, I've seen your ears already. I'll arrange a scan before see me in clinic so that you only need to come here once.
Yeah, I think, very valid that you even could say that the triaging process itself might even be surplus to requirement if you have high quality tech and you integrate it into your healthcare system effectively. Yeah, thanks very much for coming along, Mr. Coulson. Really appreciate it.
Thank you for the invite.
Thank you. So, Jeffrey, did you fancy taking us through to the next speaker?
Oh yeah, thank you. So the next speaker is Dr. Kedgley. Dr. Kedgley is a reader in orthopaedic biomechanics at Imperial College London. She also taught me as I intercalated in biomedical engineering, which I very much recommend if any med students get the chance to intercalate and get taught by Dr. Kedgley. I think she's got a very unique perspective on how doctors and people in the medical profession can sort of interact and work with engineers to produce devices. Thank you very much.
Thanks, Jeffrey. I'm just going to share my screen. Can we see that? Yes, okay. So thank you very much for the introduction. I'm glad you didn't Google too much on me, or if you did, you didn't find anything. So that's good. I guess the title of my talk is, do I need to be a surgeoneer? And I did not coin that term, but I quite like it. I think I like the idea of it, and to put forward to you today that you don't necessarily need to be a surgeoneer. So I study the amazing human hand. I am a mechanical engineer by training, and this talk is going to be a little bit different than the one you just heard from Mr. Coulson, because I don't necessarily develop products, but I have always been fascinated by how you could apply engineering to the human body and specifically to the human hand. And I think you can approach studying the hand from a lot of different perspectives, including the ones I have on the screen. And the nice thing about bioengineering is that they overlap, as far as I'm concerned, with all of these different areas, which makes my work very varied and interesting. And I think that it just depends on how you look at the problem. So if we were going to look at the human hand from a clinical perspective, you might think of it a little bit like the pictures on the screen. Maybe you might think about broken bones or doing surgery. But if I was going to think about the human hand, and this talk is about the development of engineering solutions to medical problems, I might have a slightly different perspective. And yeah, that is a digger on the screen. analogy of a digger is, I think, an excellent analogy for the human hand. It was first suggested, as far as I'm aware, by a surgeon by the name of Paul Brand, and he put forward this analogy when he was writing a textbook on clinical mechanics. So if we think about the hand in terms of a digger, we can say that the motors are like the muscles, and the motors are back there in the cab. And then we have these tendons that are going from the cab down to the end, to the bucket, to operate the hand. And you might notice that the cables will have to cross multiple joints.
Angela, are you expecting your slides to be advancing?
Oh, are they not advancing? Sorry, let's try this again. They're not. Oh, there we go. Okay, now we are. Sorry. Thank you, Peter. Okay, there we go. Human hand. I don't know why it wasn't, but that's all right. So we have this old-fashioned digger structure. And the fact that the cables have to cross multiple joints means that they're very interdependent. And this is exactly what we see in the human hand. Our tendons have to cross multiple joints in order to get our hand to function properly. And that's a big design challenge from a mechanical perspective. So what can go wrong with this system? Well, as I'm sure you know, lots and lots of different things. We can get problems with the joints, we can get problems with the muscles, we can get problems with the nerves, which mean that large sections of the hand can be put out of commission. And how we might tackle these problems really depends on how you look at them. So how I look at these problems varies dramatically with how my clinical colleagues do. And I'm going to just talk about a few different research studies that we have done and how they came about, to provide you with some examples about how you can get involved with this type of work. So in terms of biomechanical factors, there are, as I mentioned, there's a large number of segments. There's a high interdependency of the joints. And I would argue, compared to joints like the knee and the hip, we don't have as good documentation really about how these joints function. So although we can easily see the hand and we can see how it moves, it's actually quite difficult to assess functionally. And then in order to do that, we need to have an understanding of how everything works together. So one of the studies that we did quite recently is a study that came about by a proposal from some clinical colleagues at Chelsea and Westminster Hospital. And they were interested in what at first inspection might seem like a very simple problem. So they were interested in whether round-bodied needles resulted in a different strength of tendon repair than cutting needles, because they'd always been taught that you should use one type of needle for one thing and another type of needle for another thing. And they thought, actually, never actually seen this tested on human tendon before. And so what seemed like quite a simple question, they came to us and said, how can we test this? And we said, well, actually, we can do a simple materials test. We can put this in an Instron machine. We can have you do the surgeries, because as engineers, we're not trained to do that. And then we can help you test your hypothesis. So this study was really clinician initiated and clinician driven, and the clinicians did everything apart from running the machines, which was amazing. And we found out that there wasn't any difference in the failure loads, but there was a difference in the way that the failures happened. And we hypothesized that that's because there's a difference in the way that the needles actually pass through the tissue, which hadn't been seen previously. So clinician initiated studies are always excellent. And I think that if you have a question and you don't quite know how to find the answer, one of the things to do is to approach somebody and say, look, I have this question. I don't actually know how to find the result, but maybe you can help me. Maybe you have equipment that I don't have. Another study that is kind of similar is that we were looking at the stability of the joints in the base of the thumb. And the base of the thumb is quite a small joint, and it is primarily held together with the ligaments. And what we were interested in is which of those ligaments provides the greatest amount of stability. And as engineers, we could put forth a proposal for how we could test this. But what we really needed is our clinical colleagues to be able to do the dissections, to section the ligaments, because they have a much better understanding of the anatomy, particularly around these small joints, and to help us interpret the results. And so we did this study looking at which of the ligaments is most important. And what we found is that 2 of the ligaments of the 4 that we looked at were much more important in terms of providing stability. So in this case, the clinicians had a hypothesis and helped us with the study, but then the analysis and the testing was really done by the engineers. And then we can also say, okay, well, we have this funny joint at the base of the thumb, and it relies on these ligaments for stability because it doesn't have a lot of bony stability. And so we see a lot of osteoarthritis at the base of the thumb because of this. And so another thing that we were interested in is how much of our stability is actually coming from the bony surfaces and how much is coming from the ligaments. And by looking at the ligaments in this materials testing machine, we can see how much stability is lost. But what is the effect of different joint shapes? And so this was a study that we did looking at joint shape through something called statistical shape modeling. So statistical shape modeling enables us to take a population of shapes and then look at the factors that are causing variance in those shapes. So we can classify those variants and see that there are differences in the curvature of the joint. There are differences in maybe the width of the joint or the tilt of the joint. And in this case, this study was something that we as engineers were interested in because we wanted to have a better understanding of how the joints functioned. And we were able to do the analysis, but what we really needed then at the end of the day was some insight from the clinicians about what this actually might mean clinically, because we can do all kinds of maths, and that's great. But if it doesn't have clinical impact, then in some ways, what's the point? So in this case, we found that changes in the dorsal curvature may affect the ability of some of the ligaments to restrain the joint from radial subluxation, and that might result in formation of osteobites on the volar beak of the joint, which then has implications for progression of things like osteoarthritis. So by doing the mathematical analysis, but then collaborating with the clinicians to look at what is the actual clinical meaning of this, we get better insight into what our results may potentially mean. Other technologies that we use within my research group include optical motion capture technologies. So these are the same types of technologies that are used in the video game industry to look at movement to create characters. And we use these to monitor movement of participants in the lab doing studies. And so we had taken these systems to the clinic and worked with hand therapists to see the ways that we can assess people during rehabilitation. And we have also used the treatment of hand pathologies is very common. It's very cheap. It's non-invasive. The difficulty with splinting is it's not always clear what the effect is biomechanically. So is the splint actually doing what you want it to do in a mechanical sense? Is it just providing kind of a protective or reassuраtive effect for the patients, which is good, but not necessarily the full effect? Or is it just a kind of placebo treatment of some sort. And so this was a study that we did in collaboration with a research group at Oxford and another one at Leeds, looking at instrumenting a splint, so putting pressure sensors underneath the splint surface, using EMG to monitor the muscle activity. And then also using those optical motion capture markers to look at how the joints can determine. The longer term objective is to use these sensors to look at another key technology that we use within my research. Another key technology that we use is something called physiological joint simulators. So physiological joint simulators give us a controlled way to compare different surgical repairs. So what we do is we basically create marionettes out of specimens by attaching cables to tendons, which we can then pull on, providing the force that might be applied by the muscles in vivo. And so doing this enables us to recreate motions that we might see in daily living. And that enables us to do things like surgical repairs, test the effect of those. And while you couldn't then ask a patient to go home, see how the recovery goes, come back, have a different surgery, see if that one is better than the last one, we can do that with these types of testing simulators. So the engineers have designed this device, but then the clinicians usually come to us with a clinical question saying, I'm interested in this particular surgical repair. Can we test this and see what the effect is on muscle forces, for example? So in the latest version of our simulator, we control 11 different muscles, mostly the extrinsic muscles of the hand and wrist, but we're now working at the addition of intrinsic muscles as well. And so, yeah, as I said, we had cameras, same cameras tracking the movements of the joints. We tell the system what we want the hand to do. We then have motors that are pulling on the tendons, which produce movement. And we have a computer program that optimizes what those muscle forces are. And in doing so, we can look at simple things. So this is just looking at the difference in muscle forces that are required to produce circumduction of the wrist. And we can see that even in this simple example, we get different muscle forces depending on which direction you rotate your wrist in. But we can use it further to look at things like surgical repair. So we did a study looking at surgical repair for thumb osteoarthritis. And we compared a number of different surgical procedures. And the small joint at the base of the thumb is, if you get osteoarthritis, one of the most common ways to fix that problem is to do a trapeziectomy. And so you just take out the trapezium because if it's not there anymore, it can't hurt. But from a mechanical perspective, when I tell this to a room full of engineers, they all go, my goodness, what? I mean, surely that doesn't work anymore. You've just taken a bone out of the hand. How can you possibly function normally? And I mean, amazingly, people do, and it works pretty well, and it's cheap, and it's relatively simple compared to some of these other surgical techniques. But what the surgeons were really interested in was, what is the effect of this on the stability of the joint and on the muscle forces? Because if you do a repair and you're, say, increasing the muscle forces that are required in order to perform particular activities of daily living, you then may have knock-on effects in terms of long-term capabilities of your patients. So we did a trapeziectomy. We then did a series of repairs. And what we found was that there was a difference in the muscle forces that were required to produce motion at the wrist as a result of a trapeziectomy, which you may think might have absolutely nothing to do with movement of the wrist itself. And then my final example is one that again was proposed by a clinician. So this clinician came to us and said, you know, we do repairs of distal ulnar fractures, and there's a whole plethora of different plates out there on the market. But how do we know which one of these is going to be best? There's lots of different anatomical plates. Commonly, these plates cause irritation to the ECU tendon, and so they usually have to be removed after the bone has healed. But that means you have to do a second surgery. So is there a safe zone in which you can apply these plates so that you don't maybe have to do a second surgery? And which ones of these is going to be most adaptable to different bones? So again, by doing a biomechanical test, we could look at defining a safe zone in which you could place these plates. And we were able to provide some ranking of which ones of these plates might be most adaptable for different patient populations. So I guess, I mean, the original question was, how is it that you can actually get involved with this type of work? And I'd say, similar to some of the messages that Mr. Coulson gave earlier, I'd say being imaginative is important. I mean, if you think you have a crazy idea, but you're not quite sure if it makes any sense, or you're not quite sure how to carry it out, do talk to other people that don't necessarily have the same skill set as you do. Because I think we don't have, as engineers, the skill sets of clinicians, which is why we love to collaborate with clinicians. But equally, we do have equipment and skill sets that maybe clinicians don't have. I think providing perspective is really important. So like I said, engineers, we can do math all day, but if it doesn't have clinical insight, then it doesn't have impact. And really what we're interested in is actually producing impact from our work. And by working with clinicians, we can do that. And I think you provide valuable input. And I think the biggest thing is to participate and to want to be involved. So in some ways, it's not so much, you know, how do I find a way to be involved? It's, do you want to be involved, and do you have the time to be involved? Because obviously a lot of these things do require some time commitment, but we love having clinicians collaborate with us. And I think that whether that is, as Jeffrey said, part of a program like a IBFC program or an intercalated PhD, or whether that is as a fellow or as a consultant, when you move upwards in the ranks, whatever level you're at, it's what is your interest? And if you're interested in solving problems and in collaborating with other people, then it's really just about using your own skill set. And you don't actually have to be trained in everything to do so. So yeah, thank you very much. I think that is it from me.
Thank you very much, Dr. Kedgley. We've got one question from Anthony here in the chat. I'll read it out loud just for the purpose of recordings and things. So he asks, hi, Dr. Kedgley, thank you for the interesting introduction into the biomechanics of the hand. You mentioned clinician-initiated studies. I was wondering how in depth do you have to understand the anatomy / clinician aspects of a hand in order to carry out investigations as a clinician? How do you deal with the medical terminology that's needed to communicate with clinicians effectively?
That's a great question. So yeah, you have to learn the medical terminology in order to collaborate with clinicians, because I think everybody has to be working on the same page. And so some of that is about learning basic anatomy. And I think you don't have to be an anatomist. So there are people who will study their entire lives. And even now, if I have a consultant come into the lab and I ask them to do a dissection of something that is not something they commonly do surgery on, there will be a textbook on the table, and that's fine. But it is about knowing enough about the anatomy of whatever structure you're looking at in order to be able to have a conversation where you can use the same words.
Thank you so much for talk today. Yeah, it's really, really interesting.
Can I ask a question, if you don't mind, Dr. Kedgley? It's kind of the reverse to what Anthony's asked. I wonder, how do you deal with clinicians trying to speak your language? Because I think that it's probably, from my experience, perhaps easier to Google something or look at a textbook, and I imagine that concepts in engineering are probably far less readily digested and available. So I'm wondering, how do you communicate with clinicians effectively using your language?
That's also a good question. I think it depends on the concept that you're looking at. A lot of concepts can be, I mean, we get a lot of practice in trying to communicate our findings to groups that are not necessarily the same as us. So whether that is members of the public, whether that is clinicians, whether that is patients, we always try to have different ways of explaining concepts so that people can understand them if they don't necessarily have a degree in engineering. And that's fine, but I also think it's a conversation, it's a two-way street, right? And some clinicians are going to have lots of knowledge about whatever concept, and some aren't, and that's okay. It's just about the individuals.
Fantastic, thank you. Makes sense.
So much. So our next speaker is Professor Peter Childs. Peter is the lead in engineering design and the founding head of the Dyson School of Design Engineering at Imperial College London. I watched an amazing talk by Peter to the bioengineers while I was studying there for a year, and he's got a very unique perspective. He's worked on a huge number of different projects, not all medical related, and so I think that's going to complement the three speakers we've had today with a doctor, a bioengineer, and much more of a pure engineer. So thank you very much.
Thank you very much, Jeff. You said lots of nice things there. And hi everyone. And it's great to actually follow Chris and Angela, because they've set the field very well. So Michael and Jeffrey have put the program together well. Chris has challenged us to say, yeah, you could do little sketches where all of the technology is missing, but you've got the essence of the idea. And then Angela has added to this by showing sort of the clinical world connecting to the engineering world. So I just want to build upon this a little bit. I do have a slide deck, but I'm not necessarily planning to show it all or give it all. And Jeffrey and Michael have permission to stop me at any stage, as actually all of you have. So if you want to ask me questions, I really don't mind. We got just under 30 minutes, and I don't have to present my deck at all, actually. So I'd much prefer a conversation. But I will kick off with something, and we'll see how this goes. So all being well, your screens have turned black with my QR codes in the middle. I think the QR codes work. And Jeffrey said that I had done lots of stuff. And so on the right-hand side, you'll just see some of my designs. I've done lots of engine bits. So there are about 55,000 jet engines and gas turbine engines out there generating our power and flying us around. And nearly all of them have engineering related to work I've done at some stage. I've not designed an entire engine. It takes about 800 person years to design one of these things. But I've designed engine bits. I've also run a jumper business, alpaca knitwear, and I have done half a dozen or so medical products over the years, including continuous positive airway pressure, ventilators, if you wish, for premature babies. So, lots of people, surgeons describe to me that you only do 4 things in surgery. You move stuff, you chop stuff, you inject stuff, and you remove stuff. And we have a way in design called functional analysis. And if that's all there is to surgery, then there are tools from other domains which can really help. And so whilst I have done lots of things, it doesn't really matter. So I'm actually just going to move on from that. I've had the privilege of being involved with this program, Innovation Design Engineering. You may have come across it. It's run jointly between the Royal College of Art and Imperial. And these images on the right-hand side, you might have some of them in your home or own them, or your parents will have owned the Nokia phone at some stage. But we've had about 600 graduates from that double masters between the two colleges. And they really do, they do lots of precision analysis. They are always designing for people. And they're always prototyping, not always physical prototyping. The examples on the right-hand side, you got Alex Kaligoulis with the Sea-Doo. The 3 original engineers for the Dyson company came from South Kensington, or their education at South Kensington. And as I say, Alistair Curtis working or leading the design group at Nokia during its glory years. Lots of prototyping, but sometimes it's pretend prototyping. You pretend you have a gadget and you pass it to somebody else and see how they react, and you get into role play. So physical and non-physical prototyping. And above all, this whole program is about being progressive with purpose. And something I know about your domain is that you care. And so this last one will absolutely resonate. A rhetorical question, and if you've seen talks from me before, I ask this question: when do you get ideas? How do you get ideas? Where do you get ideas? And some people will answer in bed and sleeping, other people in the shower or in the bath. Sometimes people will answer in boring lectures. I'm not going to lecture too long, so try not to bore you. And these are known as the B's of creativity. And as I put this list up, you'll probably pick up upon the common facet of these. And that is, and this is backed up in psychology and in neuroscience, and that is that we have ideas much more effectively and with much more fluency when we are relaxed. Now, it is a few to several times factor, and something that we're always encouraging anybody who wants to have ideas. It's to make sure they got that mix of concentration and relaxation in their life, and above all, that you write down your ideas as you have them, because we know how short our short-term memory is. 2 to 30 seconds, and then the thought is gone. So write it down, or do the email to self, the note to self, to capture that idea, and then go back and review them. Now, this is not one of my designs, but this allows me to talk about what design is. And I see design as the transformation of an existing state to a preferred state. Some of you will have read about or seen films about modern day piracy on our seas. And this is it's more than a concept, but this is work that Rolls-Royce, the aero engine manufacturer, is doing on the future of shipping. And so we know how we're moving our containers about today. Is this the future? It's transforming things from one thing to another. So I'll just say that as a bit of inspiration. I do want to say that the traditional inventor approach, where you have your bright idea, maybe do some sketches, some calculations, write some ideas down, then look at what you've got. And if you don't like it, you go back and do some more sketches and calcs. This process is as valid now as ever it was. And just to prove that point, what I'm showing on the right-hand side is Neil Barron's work. He has a desk just like many of us, and he does do sketches, and his desk is covered in artifacts and bits of steel and bits of fabric and Kevlar. But these are his sketches. And the Lightlock company has had 3 or 4 times manufacturing boosts over the last couple of years. They're doing these very robust bite locks with great resistance to attack, and going great guns. And absolutely, Neil follows this very traditional approach to great effect. You'll have heard of design thinking, perhaps, where we sort of meander all over the place before we get to something that you might see as a linear flow process. But even this meandering has some structure to it, perhaps, or certainly phases, a research phase leading to some conceptual ideas, and then getting into the more detailed design. But there are very 21st centuries and very 21st century contemporary approaches too, which look much more systematic, such as this distorted V diagram. And I will supply this deck to Jeffrey, and he's welcome to distribute it. But I wanted to show some examples of ideas that have made it. So whether you respect these products or not, I just wanted to show you things, because just like Chris showed, you can have a bright idea where you're adapting an existing product, don't know quite how you're going to get there, but then you, through collaboration, you can absolutely do that translation between the idea and the embodiment of the idea. So Doppel are using a beat device which sits on the inside of your wrist to either calm you down, depending upon the vibration frequency, or excite you. Not from the medical domain, but I wanted to show this. This is Safety Net, who using acoustic gadgets and light gadgets, which you attach to the trawler nets. You may well put 20 of these on a trawler net, and these are reducing unwanted bycatch, or the catching of unwanted fish, by very significant amounts, you know, up to 90% on occasions. So I'm sure you're all aware, so much of what's pulled up is unwanted, and by the time it's pulled up, it's damaged and you can't sell it, so it just gets slung back overboard. The safety net technologies are on the verge of transforming our fishing industries. I wanted to show you something that was non-physical. This is Farewell, and Dan Garrett, again graduating from Imperial 5 years ago, 2016, 2015 or thereabouts, had this idea of young people like him not doing wills, and could, you know, what were the barriers to that? And so explored whether it was possible to do it all online. And now Farewell employs several hundred people in Clerkenwell, a very large legal practice. And so many clients have been through their system. You know, do check it out. I wanted to show you this because it's, some people think of design engineers doing everything that's looks like prototype and the works like prototype, very physical. But ideas need not necessarily be physical. And of course, Farewell were there at the right time, you might suggest, and they've had a very successful last couple of years. Another non-physical company is Curio, an app. Many of us have an idea of doing an app. Govind Balaksharan came up with his idea for people wanting to consume audio, but they want it to be narrated in a high-class way, and they want to choose. And so by working with various publications, was able to push out this idea, develop it, and now has 500,000 clients. Something you may have seen, the Orbel product. We've all done it. We've grabbed our gel, but in doing so have contaminated our hands and the gel bottle. The Orbel product, taking its inspiration from the dog's tongue, may not quite be the analogy you want, but being able to wipe your hand over these 6 dispensers, get your sanitizer onto your hands without having to contaminate either the bottle or your hands, and vice versa. And you're able to sanitize your hands 10, 15, 20 times an hour. An extremely relevant product, which was going 4 or 5 years ago, but certainly the right product at the right time. Then jelly drops, another idea that's made it. Many of you will have loved ones with dementia, and we all know the challenge. You can you want hydration to avoid those anger moments associated with significant dehydration. And Lewis Hornby, Nick Hooton and Claudia Arnold, again from the South Kensington stable, if you wish, Imperial and the Royal College of Art, digging into what we ended up calling the chocolate box memory, this notion that if you've got a box that looks a bit like a chocolate box, people will open it no matter how late stage the dementia is. And they will just reach in and grab hold of one of these balls, pop it in their mouth and consume it, and will keep on going until all of those balls are consumed. So you need to limit them. But one of Lewis's clever ideas was colouring these so that the carer has something to say. Oh, do you like orange? Do you like green? I like green. And the next day, they may pick a different colour first. And you can have a different conversation about colour, but keeping the carer in mind as well as the cared for person. So, always keeping the stakeholders. Jeffrey was kind enough to say I do lots of different things, and one of our latest activities is working with Bladebug, who do these hexapod robots which clamber all over the massive wind turbine blades. These blades are can be 108 meters long, a surface area of 400 square meters, and we need to inspect these wind turbine blades and do overhaul, repair and maintenance. And the Bladebug robot is able to traverse all over these blades within this harsh environment and undertake these activities. So lots of different things. And we do use brainstorming, but there are many types of brainstorming. Use of post-its, alphabet brainstorming, where you come up with a few ideas with the letter A and then move on to the letter B. And by the time you got to Z, you've got over 100 ideas, which you can then review. And we do systematically go through the alphabet, letter by letter in order. Lots of types of brainstorming. There are about a dozen thinking styles. And I'll allude to this later on. And whilst we may have a dominant thinking style, you might want to use or try out something else. This list goes on. And I'll talk about some of these. And of course, we are in the 21st century, so why not use some AI and machine learning and augmented approaches? One of the items in the list was TRIZ, the theory of inventive problem solving. Here we are, 7:13 in the evening, and I'm showing you a 39 by 39 matrix, and I'm zooming in, and yes, this is really happening. And the TRIZ methodology is a shortcut to experience. And I've just picked out a standard medical example using the theory of inventive problem solving. How can we ensure correct dosage and timing of application? Well, we all know that a liquid is easy to get the right dosage of and to dispense. But if you pop it on the eye, it goes everywhere and fills up the eye cul-de-sac. Your anatomy is better than me. But if you look at the TRIZ matrix, you'll discover that something that's improving, the thing that you want to improve is associated with duration of action by the liquid in the right place. The thing that's getting worse is the quantity of substance. It's going all over the place. And these two numbers allow us to scrutinize that big matrix, which then suggests principles of invention. So there's so many ways one might be able to tackle a problem. Is there a shortcut? Well, the answer is TRIZ gives you that shortcut. So immediately we're guided towards these principles of invention, for example, transforming the physical state of an object. And indeed, many of you will be familiar with the idea that eye drops, you don't want them just to hit the eye and go everywhere. So maybe having a product which is liquid for dispensing, but the moment it hits the eye and the heat associated with the eyeball, it transforms into a gel and therefore does its useful action in the prescribed location. There is a simple tool out there called Scamper. It's an acronym, mnemonic, standing for substitution, combining, adaptation, modifying, putting to other uses, elimination, and rearranging. So you want ideas? Just think, can I substitute something? Can I combine things together? Can I adapt things? You know, maybe a few ideas for each of these provocations. I just got 3 or 4 examples. You know, substitution, if you've got limited sight, do you want to be putting your hands near hot surfaces on the cooker? And Menno Crozen, again from Imperial, came up with the idea of substituting the materials and indeed the pot. So the cooking pot is safe to touch because it's got thermally insulating materials, but the cooking pot is actually the control, and you twist it to make it warmer, you twist it back to make it colder. Putting to another use, so in the Scamper provocation, the P is for putting to other uses, you know, light as fashion. And again, this is Elizabeth Hyde. And elimination, again, part of the Scamper provocation. And the Luwatt student idea became a spin out, has become a good business. They have eliminated, they do the waterless toilets. And perhaps you've been to festivals in the UK where these toilets are available, but they've also had good market penetration in countries such as Madagascar. Here's one that did not work, but Gareth Jones, who was the technical director at Dyson, he's had so many great products. Maybe having one that didn't quite work isn't so bad after all. But the idea here was a dual rotating drum with reversal, so better cleaning action. But they released this product into the market 2004 or thereabouts, and very quickly there were complaints. So people's clothing, you know, with tassels and strands were getting caught up, and it really didn't work. They pulled it out, I think, after 600 gadgets had been sold. Shown you one matrix. This is a morphological chart. It's you pick up one item from each row, blend them together or synthesize them as one idea, and then you make another selection. So this is the morphological chart for society. We have them for things like hospital organization. Might worry you in case you think, are our managers really trying these things out? I talked about augmented things. Well, the challenge of doing a mind map on your own, well, why not use B-Link, where you pop a couple of words in or a word in, and it then analyzes 3 million Elsevier journal papers and creates what looks like a mind map in front of you, and then you can explore different links. Some of you will have great ideas and then want to produce a patent, and Simon DeWolf runs AU Alive and Patent Inspiration, and they will do heat maps showing where the patent ideas are covering information and where there are gaps. So getting that sort of AI insight around where the ideas actually are protected and where maybe they're not. If you want to learn lots of creativity tools, you can always do the MOOC, the Massive Online Open Course in Creative Thinking. Over 250,000 people have done this one now, and we're going to keep going. We've got a new version of it coming out sometime next year, but the old version's great too. Just want to finish on this one. How do you know what kind of creativity tool, creativity approach to have? And so we've been looking at this and come up with what we call a creativity diamond. This notion that you want to come up with lots of ideas through divergent thinking. Do you use brainstorming? Do you use one of these other methods? And so this faceted wheel is just suggesting to you perhaps that you might want to use morphological analysis and principles of invention and metaphor and design thinking whilst you're diverging. But perhaps when you're pushing towards 1 or 2 ideas, that you might want to use other creative approaches such as analogical reasoning, critical thinking, in order to converge towards your selected outcome. So this spinning wheel, you could just spin it at random, but or you can do directed decision making about which approach you actually want to use at a particular phase. I must stop talking there because we must have some time to wrap up. And thank you very much for listening. 18 of us are still here. Thank you for staying on.
Thank you so much. So we've got a few questions actually in the chat. We've got 2 questions. So we've got another one from Anthony, who I can invite to unmute himself if he wants to ask himself.
Yeah, sure. Can you hear me? Does it work? Can you hear me?
Okay, I'll read it out. So, hi, Professor Childs. I personally think, in brackets, feel free to disagree with me, that an engineer is great at solving problems given enough time, money, and some compromises. But how do engineers like yourself seek a problem that can make a big impact?
Okay, so I think one of the things you're suggesting is that engineering has a great heritage, and that give us large sums of money and we can design expensive cars like the Rolls-Royce Motor Company. Because there is such a great heritage to design and engineering, so often there's this sort of toolbox of approaches and technologies that we can borrow from and implement very quickly. And something I wrote down during Chris Coulson's talk earlier on was plug and play. There are just so many technologies out there that without a huge amount of experience, just a willingness, that you can adapt and exploit, even if you don't have an engineering background and big budget. So that's one of my responses. The other response is I love the collective mind. So, and I think already tonight you've had a few, well, the 2 previous speakers talked or implied about collaboration and the benefit of the collective mind. So even if one person on their own doesn't have the necessary skills, by collaborating, a small team can get a lot done. And so I find forever I'm collaborating with, I've collaborated with heart surgeons or breathing specialists or neuroscientists on things I have very scant knowledge of. And a phrase I often say is, I've never let a lack of talent or a lack of ability stop me from having a go. And that might worry you in your world in your clinical world. But the willingness to have a go at something seems to take you quite a long way. And as long as it works at the end of it, that to me is the outcome you're going for. Absolutely, some other team could do it better, but you got it working first. And maybe you got the patent and you got the company first and you got market advance first. So we often find that we get stuff working within a few days, not a few months, because we have a prototyping approach and we'll borrow equipment from other things. Like Angela showed with her mock-up of her tendon. I may be doing you a disservice here, Angela, but she showed us a very sophisticated, well-engineered equipment. But one could equally well put that together within a day or a couple of days and get something that sort of works, maybe not with the accuracy, but it's enough to give you that momentum, about whether it will work, whether it's worth getting everything made properly. Angela, do you want to kick back on that one?
No, not at all. I think it's absolutely the case that we could, do something quite simple. And in fact, the earliest versions of the simulators were using dead weights. because it's easy. You just put a weight. You don't need loads of control strategies and all this stuff. But then that gives you an idea if that might work. And then if you want something more complicated, then it's worth investing in. But you need to do the preliminary work first, for sure.
There's a company that's just, well, former graduates from a few years ago, just done a Parkinson gadget, Parkinson's disease gadget to aid movement for people suffering from Parkinson. And something that I know the people have known for a long time, if you do a drum beat near somebody with a stutter or with motor challenges, just the drum beat is enough to get them going and keep them going. And that wasn't the principle that she used, but we certainly talked about it. But she does use a beat on your skin. And they just, I think they've had an $11 million investment. But they were having their gadgets working very early on. Yes, they've done 3 or 4 years development with about, I think now about 15 person years engineering and clinical work. So it is big budget, it is huge effort, but actually very early on, with just a few person weeks effort, they were demonstrating principle with real people and real gadgets. They just weren't finessed. How do you meet people? Imperial, UCL are just great places. I love Imperial because there are 18,000 of us. Sometimes I'm going to be politically incorrect, this is being recorded, but sometimes I describe this as 18,000 techno nerds who love our gadgets and mechanisms and science and medicine. And you've got thousands of engineers who want to work with the medics, and you've got medics who want to work with the engineers. And places like the Hack Space at White City are good for this. The Enterprise Lab in South Kensington, the bottom basement of the library, it's a bit of a challenge to get in there. But there are hundreds of people associated with the Enterprise Lab who want relationships with people with medical capability. So to me, it's just about venturing into the hack space at White City, venturing into the Enterprise Lab and just chatting to a few people, attending an event, and all of a sudden you got 40 contacts and away you go. So I'm just encouraging that. And in design engineering, in bioengineering, in electrical engineering, you've got hundreds of PhDs and master's students and undergraduates and staff who actually want this relationship. So I think it's reach out.
Thank you so much. Yeah, it's an amazing talk. I felt like I've learned a lot about how to approach medical problems with an engineering mindset. You talked about Scamper and the P in that. You mentioned putting into other use. That was interesting seeing that in Mr. Coulson's sort of endoscope eye and the bike motor testing. So amazing seeing kind of the links between two very different sort of jobs and areas of work. Yeah, so of course, thank you to all of our speakers. I think that more or less concludes the event, unless anyone else has any other questions. Dr. Michael Edwards has been called away. He said he's on call, so I don't think he'll be here for the end. But thank you so much to our speakers. I've learned a lot. A recording will be available, so we can go through the slides slower in our own time if we need. A few points I noted were that some things we could do is writing down our ideas quickly, drawing them again and again, improving this iterative design idea I think came up in quite a few of the talks, and also find the experts. We're not supposed to be experts in everything, and so find the people who know basically, and you only need an idea. Yeah, thank you so much to all of our speakers and everyone for coming along. We'll email out a link or let people know where and when a recording will be up. Thank you.